And they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun. But they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape, and that's a black hole. They're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon, and if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison, a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. There's one called the Crab pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
They remain stars for 100,000, at most 1 million years, and they'll explode and become a supernova. If you're more massive than that, they will not explode because the gravity is so strong that it cannot explode against the strength of the gravity, and it collapses into a black hole. So we expect black holes to have slightly less mass, somewhat less mass than the most massive stars that we know how to make. So if you have 100 times the mass of the sun star, it'll lose half of its mass over its life, and you have a black hole that's 30 times the mass of the sun or 50 times the mass of the sun. Fine, put a pin in that. In the centers of galaxies, there are supermassive black holes, hundreds of thousands, millions times the mass of the sun. And they're supermassive, and they're black holes. We call them supermassive black holes because that's how we roll as astrophysicists. Well, could you have black holes somewhere in the middle of these two extremes? We do not know a phenomenon that will give you a black hole that's in between, that will birth a black hole that's in between these two categories. You can make a black hole that eats its way there, but we don't know how to make one. And we think, my colleagues who've done this, think they've discovered a black hole that is sitting in this sort of netherworld where there's no evidence that it ate to become that massive, and we don't know how to explain it by the formation and death of stars, and is nowhere near the supermassive black hole in the center of the galaxy. So it's the frontier of research of a physically impossible black hole. So scientists don't use the word impossible unless it's violating a known law of physics. You can say it is a black hole that comes from if it comes from an object, it is an object we know nothing about and have yet to discover. We're not going to say it's an impossible object. Every time we point the telescope to the universe, we find something that we never predicted or understood.